let us look at some other aspects of circuits. So another type of circuit element is a capacitor. A capacitor stores charge on its plates. So in a circuit it looks like this, and normally it will get connected across the battery via a resistor. And as the battery provides a current in this circuit, so the current flows from the positive terminal of the battery through the circuit this way and ends up at this point. Well, the capacitor doesn't let current flow through. There is literally a gap between the capacitor plates. There is nothing in here. But the positive charges that travel get deposited, or one by one, on the capacitor plate. Well, this one positive charge on this plate will attract a negative charge on the other plate, leaving a positive charge unpaired to keep on going. And the current will keep on flowing. A second charge will be deposited on the capacitor plate, which attracts a negative charge. And this keeps on happening until the capacitor gets filled up. The capacitor is fully charged. Now, what really happens with a capacitor is that the charges will have a harder and harder time depositing on the capacitor plate because there will be electrostatic forces acting between these positive charges. So the more positive charges we put on here, the more electrostatic force there will be between them, and it will be less and less easy to deposit charges on the capacitor. So when the capacitor is fully charged, it doesn't take any more charges, then it acts as a circuit breaker, so the current cannot flow anymore through this circuit. All right, so capacitors have a certain capacity for how much charge they can store, and that is also a function of the voltage that is applied across the capacitor. This capacitance has the symbol C and is measured in farads. And usually capacitors are really small. They have units of microfarads, so that's 10 to the negative 6 farads, or nanofarads, which is 10 to the negative 9 farads, and so on. So when we talk about capacitors, it's very seldom that we'll say, oh, the capacitor has a capacitance of 3 farads. That's really unheard of. The equation that relates the amount of charge that's stored on a capacitor to the capacitance and voltage is Q equals CV. So there are different shapes of capacitors. One of them is a parallel plate capacitor, so it's just what I drew before. It looks something like this. And the capacitance of a parallel plate capacitor is epsilon naught A over D, where epsilon naught is the permittivity of free space, 8.854 times 10 to the negative 12 farads per meter. A is the area of one of the capacitor plates, so it's, if this were a three-dimensional thing, then it would be the area of this plate, and D is the separation between the plates, so it's this little distance between the plates. So capacitance is a function of the shape of the capacitor, and epsilon naught, the permittivity of free space. Capacitors have a positive plate and a negative plate. And let's say that this is the positive plate and this is the negative plate. And we know that an electric field will be formed between these capacitor plates, and the electric field goes from the positive plate to the negative plate. And the equation for the electric field is potential difference divided by D, where D is the separation between the plates. But then if we use Q equals CV, then V is actually Q over C divided by D. And if we use for C this the capacitance of a parallel plate capacitor, then substituting things, we end up with Q times, well, I guess I'll write it, Q divided by epsilon naught A over D divided by D. So that is going to end up being Q over A divided by epsilon naught. And Q over A has symbol sigma and is called surface charge density. So in here, Q over A is sigma. So the amount of charge stored per area is the surface charge density. So the electric field between capacitor plates, we start out with the generic equation of potential difference divided by D, and we end up with sigma over epsilon naught, which is the surface charge density divided by epsilon naught. So that's what we have over here. Now, capacitors are useful because they store energy in their electric field, and the energy they store is 1/2 CV squared, and of course if we substitute C from here with Q over V, then we end up with 1/2 QV. If we substitute V as Q over C, then we end up with 1/2 Q squared. I don't know, another equation. I guess I can figure it out. So if I substitute C with Q over V, then I end up with 1/2 Q over V squared, which is 1/2 QV. If I substitute V squared, so I have 1/2 C, and V squared is Q over C quantity squared, then it's 1/2 Q squared over C. So there are 3 equations that we can use for the energy between capacitor plates, depending on the 2 of the 3 quantities that we have. Now, in order to change the capacitance of a capacitor, we can insert what we call a dielectric between capacitor plates. So let's say that here is the capacitor. I'm making it wider here. I can insert a material between capacitor plates, and this material is a dielectric, and it has a dielectric constant kappa, so that the new capacitance will be kappa times C, where kappa is a dielectric constant. Now, this dielectric constant is greater than 1, so that means that the new capacitance with a dielectric in it is going to be greater than the capacitance without a dielectric. Now, there's 2 special cases for this. So when a dielectric is inserted between capacitor plates and the capacitor is fully charged but not connected to anything, so let's make sure that this capacitor is fully charged. Let's say that it has originally capacitance C, and then we're going to insert a dielectric between the plates. So here's a dielectric of dielectric constant kappa, and the capacitance will be C prime. Then we want to know how the voltage across the capacitor changes. So in the first situation, we had voltage V, charge Q, and of course capacitance C. In the next scenario, the charge didn't change because we didn't provide it with more charge. The capacitor is the same in both situations. But now by inserting the dielectric constant, we have a higher capacitance, and that is kappa times C. So then what happens with the voltage? Well, voltage in this situation is still Q over C, but it's C prime here. So Q is the same between the 2 scenarios. So I'm going to write it as Q. C prime is now K times C, which is then less than Q over C, which is what we had without the dielectric. So when we're inserting a dielectric between the plates of an isolated charged capacitor, the voltage across the capacitor decreases. The other situation is where we have a capacitor in a circuit. So let's just have a battery connected to a capacitor, and the capacitor is fully charged. And then we insert a dielectric between the capacitor plates. So the voltage stays the same because we have the same circuit. Let's see what happens. So there's a dielectric. So in the first scenario, I have Q, C, and V. In the second scenario, the thing that stays constant is V. We know that C prime is Kc. So then what happens to the charge? Well, charge prime is C prime times V, which is Kc times V, which means that Q prime is going to be greater than Q. So there will be more charge stored across the capacitor that has a dielectric between its plates. Now, just like resistors, capacitors can be added in series or in parallel. So let's look at capacitors in series. So here we have 3 capacitors connected across a battery. And let's say that the battery has a voltage V. We have capacitor 1, capacitor 2, capacitor 3. In series, if we remember from the resistors, there will be the same current flowing through the circuit. Well, since current is delta Q over delta T, we'll say that all of the capacitors will acquire the same charge in series. So this capacitor will have charge Q, this one will have charge Q, that will have charge Q. And maybe there's 2 positives on both of them, 2 negatives on both of them, like that. So even though the charge is the same, we remember that the voltage drop, the potential drop across the capacitors will be different. So this is V1, this is V2, and this is V3. But V1 plus V2 plus V3 has to add to the voltage given by the battery. So we can use this equation, Q equals CV, and solve for V. So V is Q over C. So Q over C1 plus Q over C2 plus Q over C3 is equal to Q divided by the equivalent capacitance. So we divide through by Q and end up with 1 over C equivalent in series is 1 over C1 plus 1 over C2 plus 1 over C3. So the theory is the same as the theory for resistors, but what is different is the relationship between the voltage and the capacitance. Remember that for resistors we had Ohm's law where V was IR. So V and R were directly proportional, whereas V and C are inversely proportional. So that's why we have the inverse relationship. So here I'm summarizing the observations we made before, how capacitors add in series, the fact that the charge is the same on all series capacitors, just like the current was the same in all series resistors. The voltage drop across the series capacitors is different, and they add up to the EMF provided by the battery. Let's see how capacitors add in parallel. So let's have one capacitor, capacitor 2, 3 across a battery. So this is voltage, this is capacitor 1, capacitor 2, capacitor 3, And it is pretty clear that capacitor 1 is connected straight across the battery, capacitor 2 is connected straight across the battery, and capacitor 3 is connected straight across the battery, which then means that the voltage across capacitor 3 is V, voltage across capacitor 2 is V, and voltage across capacitor 1 is V. But then charge will distribute itself differently on all the capacitors. So I guess I should make the minus signs more like minus signs. Like that. And I need to bring the capacitor back. So C1. So let's say that capacitor 2 can take 3 charges, and I have my charges in the wrong direction. So this is the positive end. That should be the positive end of the capacitor. So let me go back and erase things. So here's the capacitor, here's the other capacitor. So this will be the positive end. Plus, 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 minus, minus, minus. 2 minuses here. Let's say that this one can take 1, 2, 3, 4. 1, 2, 3, 4. So the charge on the capacitors is going to be different. We have charge Q1 here, charge Q2 there, charge Q3 over here. But the sum of all these charges has to be what the battery gave off in the first place. So we can say that Q1 plus Q2 plus Q3 is equal to the charge that the battery gave. But we can substitute Q as CV, so then we have C1V plus C2V plus C3V is equal to the equivalent capacitance times V. Dividing through by V, we end up with C equivalent in parallel is C1 plus C2 plus C3. So again, the theory is the same that we had with resistors, but it's the relationship between voltage and capacitance and voltage and resistance that is backwards from one another. So here's the summary of this. Capacitors in parallel add as C1 plus C2 plus C3. The charge on each capacitor is different. The voltage is the same. Now, to measure current and voltage and resistance, we use various meters. Ammeters are used for measuring current. They have very little resistance and have to be connected in series in a circuit. So we would have a circuit with a resistor in it, let's say, and then a battery. We would insert the ammeter in the circuit. With voltmeters, voltmeters measure potential drop, and they have very high resistance and have to be connected across a circuit element. So if we have a resistor and a battery, and let's say that we wanted to measure the current, so we have the ammeter in series, the voltmeter has to be connected in parallel with the circuit element. So this voltmeter is measuring the voltage drop across this resistor. So always connect an ammeter in series because it has very low resistance, and connect a voltmeter in parallel.